I am Kaustav Datto. Today I will briefly describe some special distribution functions, mainly binomial distribution and normal distribution. A random variable x has a binomial distribution and it is referred to as binomial random variable if and only if its probability distribution is given by probability x equal to x is equal to ncx p to the power x q to the power n minus x for x equal to 0, 1, 2 up to n. Binomial distributions corresponds to n number of trials in which the random variable x corresponds to the number of success. Each trial have two possible outcomes, that is success and failure. Probability of the success is denoted by P and probability of failure is denoted by Q. Clearly P plus Q is equal to 1. So probability of getting small x number of success is nothing but to arrange x many success and n minus x many failure in n places. So corresponding to each arrangement, the probability will be p to the power x q to the power n minus x. Since such arrangements are possible in ncx ways, the total number of such possible outcomes will be ncx. Hence, the required probability will be product of all these quantities, that is ncx p to the power x q to the power n minus x. Clearly, binomial distribution is completely determined by two parameters n and p. We denote this by the symbol x is identically distributed binomial np. It can be easily verified that if x is binomial distributed with parameters n and p, then expectation of x will be np and variance of x will be npq. Many natural phenomena corresponds to the continuous random variable which is perfectly bell shaped. That means if we look into the distribution of such random variables, it will be very symmetric about the mean. Early in the 19th century, few mathematicians noticed that this phenomena occurs very frequently and they fit one curve to such bell curve and they have introduced the normal distribution function. A random variable x has a normal distribution and it is referred to as a normal random variable if and only if its probability density is given by fx equal to 1 upon sigma square root of 2 pi e to the power minus half times x minus mu by sigma whole square for minus infinity less than x less than infinity and sigma is positive. The graph of fx look like the cross section of a bell. Here along the x-axis we are taking the range of the random variable and along the y-axis we are taking the function, we are plotting the function fx. At the middle the value of x is mu and if we move further from the mu in both sides, gradually the probabilities will decrease. clearly it is described in the given picture. The parameter mu is in fact expectation of x, and parameter sigma is in fact the positive square root of variance x. The normal distribution with mu 0 and sigma 1 is referred to as a standard normal distribution. The probabilities that a random variable having the standard normal distribution will take on the interval from 0 to z can be obtained from the standard normal chart. We denote it by phi of z. So, phi z actually represents the probability such that the variate z takes on the value from 0 to small z. Note that if x has the normal distribution with parameter mu and standard deviation sigma, then the variate capital Z equal to x minus mu by sigma has the standard normal distribution. In many event or any statistical measurement, suppose we are making one sample, by the virtue of central limit theorem we can say that the sample mean, that is x bar, it is also a random variable, will identically distributed normal, and x bar minus mu divided by sigma upon root n will standard normal distributed for large n. That's why normal distribution plays one important role in the probability theory. Thank you.